Hi, thanks for joining us today. I'm here with Dr. Lawful to talk to you about the exciting work we have been doing to be able to use infrared spectroscopy to predict with high throughput and low cost metrics of soil health. This is the work we are doing at Sequester Analytics, which is a commercial analytical facility devoted to provide high quality soil data now, which, however, we know that every time we try to do high quality means that there is a lot of labor and care, which also come to a cost that often is prohibitive to the analysis. And so through a collaboration with CSU, we have been working on using FTIR, and I pass now the ball to Dr. Lawful to give you the specifics of the work.
Yes, thank you, Francesca, and hi, everybody. I'm Dr. Sam Luthold. I'm a research scientist at Colorado State University, and for the last couple of years, I've been spending a lot of time thinking about mid-IR. So when this opportunity to come up, it came up to think about commercializing this, it was really an exciting opportunity. And so we need MIR to kind of rapidly scale our measurements and the amount of data we have around soil carbon, but also a broad range of soil physicochemical properties. And we've been building this pipeline for the last year or so, thinking about this. And I'm going to walk through the methods first on the left that start with the global reference library of data and end with a point estimate with an uncertainty band for an unknown sample. So broad strokes, our methodology is we start with this global library of 30 to 45,000 spectra, all scanned on the same instrument that we have in the laboratory, a Bruker Vertex 70. These are provided by the NRCS via the KSSL library. It spans the entire continental United States. We normalize these spectra using a standard normal variate transformation. So they're comparable across our instruments. There's still some noise between instruments when we do that library transfer. And then we compress this data using a principal component analysis that retains 99.5% of the total variance within the spectra. From there, we group this 30,000 samples into a mixture of between 5 and 11 clusters of spectrally similar soil. And the clustering algorithm we use is this Gaussian mixture model. And we chose that other than something like k-means because it can detect these natural groupings of different shapes and sizes a little bit more effectively. And it gives us these covariance matrices or these mathematical descriptions of each cluster's structure that are useful for measuring how well a new sample fits into a given group. And so the core assumption that we're making here is that spectrally similar soils are compositionally similar as well. So models trained on this localized cluster, being cluster 7, should outperform a single global model of all 30,000 samples. And so when a new sample comes in, when we scan a sample in the lab and then start thinking about a new sample, we apply the same normalization and then projected it into the same PCA space, then assign it to the best matching cluster. And then I think what's really kind of interesting here and novel is that our assumption is that each analyte and each kind of set of soils responds best to a different algorithm or a different model configuration. So we've tested thousands of different model configurations for the predictions of things like soil carbon across these different clusters. We have a list of the top 1,000 model configs for X, Y, and Z. And so we take the top 5 performers for a given property, and then we train all of them within a cluster, pick a winner based on cross-validation statistics, and then fine-tune that. And this gives us a point prediction for each sample that is cluster specific using the best possible algorithm for that sample. And then, point predictions really aren't enough. We need to know how confident we are. And I think in a commercial setting, that becomes even more important, especially when we start thinking about things like MMRV. So we've developed this uncertainty quantification pipeline that's modeled off of some previous work in MIR as well as just broad chemometrics work, where we train a separate model, a random forest model, to estimate the prediction intervals by learning patterns of model residuals. And so we don't train it on the values themselves, which would give us the range of possible values for a spectra in this really wide interval. Instead, we use the residuals to say, what is the probability that this sample is correct? And so this produces tighter intervals. We're more confident that our sample falls between these. And then we calibrate these intervals using this conformal calibration methodology to make sure that our stated 90% confidence intervals actually capture 90% of the true values. And if it doesn't, we apply this small correction to make sure that for the population of samples, 90% of them are falling within those true population intervals or confidence intervals. Finally, then we check whether we're even qualified to make a prediction on these samples. So using the clustering structure from earlier, that covariance matrix from the Gaussian mixture models, we measure how far a new sample is from the typical training samples. And then anything in the extreme, anything in the 99th percentile of distance gets flagged as a potential outlier, which is a quick way to spot problematic samples and be transparent about our prediction ability. And so this pipeline has worked pretty effectively, and I think we can make really nice predictions using it. And so there's a couple of examples here in the middle. The first, in this top image, is something I think Francesca and I have both been really excited about. And it's thinking a little bit more beyond physicochemical properties and into some of these soil health tests. So here we're looking at mineralizable carbon predicted via mid-infrared spectroscopy. And we see this really nice agreement between our observed and our modeled mineralizable sea. And this is from ag sites across the central United States. And so I think this is really indicative that MIR can both do the physicochemical, but it can step beyond that and capture some signals of these soil health properties that I think we all agree are really kind of key to better understanding our agroecological systems. There's additional considerations to make here. In the middle, we're modeling texture, and this pipeline also has the ability to adapt to property type. So texture is compositionally bound, right? It has a mass balance where it needs to add up to 100. And so we can add things into this like an inverse log ratio. That means these samples will always add up to 100. It knows that it has that boundary. pH is the same way, right? We can never have a negative pH or a pH that goes above 14. And so building in that kind of domain expertise knowledge into these models, I think helps constrain them a little bit more. And then just to prove this point that I kind of tried to illustrate talking about the uncertainty metrics, we have these residual based uncertainty methods that give us these really nice error bars. So we're looking at organic carbon predicted, I think is on the X. It's a little hard for me to see on my screen. Observed is on the Y. And we get these error bars that tend to overlap with the one-to-one line. And at least 90% of them do because of that conformal calibration. And when we look at the residuals, you see this really nice distribution of residuals. It's kind of randomly distributed. So we think that this is a really viable way of doing some of this wet chemistry replacement work. I think there's a lot of really exciting directions to go within MIR that allow for, quantifiable error and robust predictions. So I'll hand it back to Francesca now, but thank you.
Yes, and again, we are here working in the commercial space, and so we care as scientists to provide accurate data, but we understand that the commercial space will only work when those accuracy is accompanied with a affordable price. And so what we are excited about is that actually combining conventional with FTIR, we can reduce the cost without actually having to reduce our accuracy. And so that's what we hope to offer. We are looking now into moving, and that's also the other thing I want to point out is acknowledge the grant that enabled this work is an NSF engine grant that is designed to do this how do they call it, transfer of knowledge from R&D to commercial space. And so it's kind of, for scientists like us is exciting to be able to put our science to fruition so that also in the commercial space, high quality data can be made affordable. And so if you are interested in that, please contact Dr. Samantha Mosier or info at Sequester. If you are interested more in knowing more about the science and the method and what we are doing, contact either Sam Lawful or I at Colorado State University. Thank you.
Everyone.